our group, analytic group, was organized back in 2013. 2013. Yeah, 2013, because I joined Vanderbilt about 2011, and so 2013, actually, Rachel introduced me to a group of hers, and she had a very organized professional group already. And then she so good that, hey, Christine, come on in. So we joined together, and we keep on meeting, and she is like very supportive and give us direction where we should go. So that's why I'm saying that tonight is very, very special for me, because I very, very miss her.
I love.
And the reason also why I become friends with Rachel, because we used to work together at Vanderbilt University Actual Center. And so we, at the same time, we work on analytics, we work on data. And so Rachel really, I learned a lot from Rachel, because to me, healthcare is a new profession for me. I used to be economics. I used to be in economics, and so healthcare is like a new field to me. And I learned a lot from Rachel. And Rachel actually, as you see, Rachel is a registered nurse, and she also so hardworking. If I'm a registered nurse, that's it for today. I won't go on to study anymore, but she continues to study and went to graduate school, get her PhD in epidemiology, which I never thought about. Yeah, dare not to touch those stuff. Yeah, and at the same time, she very is a data scientist, and way beyond that, she knows a lot of clinical stuff, and also a lot of statistical methodology and data issue, and how to work with data. And unfortunately, she left Vanderbilt. very, very unfortunate for Vanderbilt. Yeah. But she has her own new career and adventures in a new company. Let me see.
Perverity.
Yeah, I just know it today. Perverity. And I want her to tell everybody what the company is, how long she has been there, and what is her job there. And she, I don't know, she's the chief data scientist there. And the rest of the time, I give it to Rachel.
Thank you very much, Christine. Yeah, so Perverity is a very small company. I'm the chief data scientist because I'm the only data scientist. And what we do is we help malpractice insurance providers figure out who is a risky, less risky, or a more risky doctor to sell malpractice insurance to. So it's like when somebody sends you something to plug into your car before they sell you car insurance. That's kind of what we do for malpractice insurance providers. All right, and then I was at the RStudio conference in January. And who here uses RStudio? Anybody? Several, okay. It was a great conference, I gotta say. It's only their second conference ever, and it sold out. And their next one is next year in Austin, Texas, and I'm gonna try to go again because I found it very useful as somebody who works in RStudio at a business, not at an academic place. So that's their market. Okay, so yeah, here's my quick thing about what RStudio is. It's an integrated development environment for R, but you don't have to use it to use this method. Okay. So I learned about this at a Keynote Address that was Di Cook, and I really liked it. And then I got back and I actually used the method like essentially the next week. This is really easy to use. It's intuitive. It makes sense to me. It makes sense to people who don't know what the heck I'm doing. It's platform independent. You can do it no matter what tool you're using to work with data. And it's valid. So I figured that more people should learn about it. And I have the links up because also the folks who they're scrolling down here. there we go, who taught it, were very generous about putting up all the information so you can get to it that way too. So that will make it good. Am I in the presentation? Anyway, you can see it. All right, and then there's also some other interesting plotting resources that I got Chow to put up there as well. Okay, so what is this method? It's a method to manage apophenia, and I also was unfamiliar with the word apophenia. But what it means is it's our tendency to see things that aren't really there in plots. So it's also confirmation bias or clustering illusion. And when you want to use this method is when you have a customer who wants to find something, and therefore they are predisposed to see something, even when it might not actually be there. And so then you want to protect them from themselves. And so that's when this is a good thing to pull out of the hat. It's when you have somebody who's like, well, I really want this to work. But you're like, I don't know. And you know, they don't necessarily understand p-values as well as they understand this. Okay, so it's called a lineup protocol. All right, so this is a photo lineup. And the reason people use a photo lineup is because it can be hard to accurately identify a true positive, all right? And so they give you a whole bunch of folks and say, we're only going to use your information if we really think that you can truly identify the right person. So in this photo lineup, which was presented on the internet as a really good photo lineup, you can see that they're looking for somebody who has one lazy eye. And they've put several folks in the lineup that have lazy eyes. And then if that's the only thing you remember about the person, you're not going to be able to pick out the right person. And in a photo lineup, the test statistic is the ability of the viewers to identify just the right person. Now, obviously in a photo lineup, we don't know always who the right person is. So this is a data lineup. So there's 20 plots there, and 19 of them are based on random data. And one of them is based on the actual data. All right, so do you think, is it big enough for you to see the numbers? Okay, so if you can see a number and you think you see one which illustrates a meaningful association between the x and the y axis, tell me which number it is.
Blue line is blue line, maybe blue line is person.
Right, so the blue line's just the least squares fit. And so then it's which of those least squares is meaningfully different from a slope of 0. Number 13?
There it is.
Okay. Okay. Oh, I'm sorry. Actual data is in plot number 5. All right. So the real data is in plot number 5. Okay, so people looked at 20 plots. Could we pick out the actual data? Okay. So therefore, is the p-value less than 0.05? You looked at 20. You couldn't find it. All right. This is a non-significant finding. So this is just showing, you know, somebody might really want to see that, but if we can't see it, then it's not real. All right. So now we got another one. All right. Here, these are box plots. This is basically a Ttest. So which one is different?
Close.
15? Okay, so we have several people who say 15. All right, so 15 is the consensus. Okay. It's 15. Yeah, all right. And that is the different data. So that is the guilty data set. So basically that's it. You guys already kind of figured out the method, right? Yeah, it's really pretty simple. Okay, but we'll talk a little bit more just because, you know, we have some time. All right, so in classical statistical inference, you have to have a hypothesis, you have to have a null hypothesis, an alternative hypothesis. Then you have to have a way to test that hypothesis. So you choose the appropriate test statistic, You understand their assumptions about the data. You calculate the test statistic and you compare it to a known distribution. And then you accept or reject the null hypothesis. So here's some really simple fake data. And we look and we say, what is the miles per gallon in two sets of cars based on how many cylinders their engines are? And that looks really very different. And so you come up with your alternative hypothesis that they're generally not the same. You use a Ttest. You calculate your Ttest, and it's very highly significant. So you reject your null hypothesis and you accept your alternative hypothesis. It's hard to understand intuitively. I mean, I'm sure many of you have had trouble explaining p-values and test statistics to consumers before. They don't get it, they don't understand it very well. And also then you get some people who just want to know, well, is the p-value less than 0.05, which is also not good because that's not really the question. The question is, can you use this information? Is this useful? Is this valuable to you? And another thing to keep in mind is that sometimes the inference is obvious, and then the lineup protocol might not be, you don't need it. I mean, if you can just put it and you see immediately, oh yeah, this is different, then you don't need it. But then if you have something where it's a lot closer, that's when you pull out the lineup protocol. Okay. So what I like about this method is that people understand it, and it's valid. And you can also communicate multiple dimensions. You're not just giving somebody a p-value. You're showing them something that hopefully they can interpret and understand how it applies to their question. But you do have to know which plot tests the hypothesis. And that can sometimes be a little bit hard to figure out. So you have to have a hypothesis that you can actually express. And then the next thing you have to know is which plot am I going to use? And then you also have to know what is null data. Okay, because if we're going to put up 20 plots, one of them's going to be real and 19 of them are going to be fake. Well, what's fake? So the other two things you have to know is, in addition to what's your hypothesis, is how do I express that in a plot, and how do I create fake data? So the paper that you can get to from the link has a table in which they show you a whole bunch of different questions, and they say, okay, this is the plot we think we would use for that. So that's one way to figure out. You also might just know because it's obvious, or because there's a plot that you were planning to show them anyway. And you're like, well, I'll just make 19 more of these, or 9 more of these, but I'll make it fake data. And so it's just clarifying here the same thing that we said before. You have a hypothesis. Hypothesis is the same. You have a test statistic. Here it's the T. Here the test statistic is the plot. All right. Then you have the sampling distribution. Here it's a known sampling distribution. And here we're just, we're just generating our sampling distribution. We're simulating data. All right, so here are a couple other plots that will test something. So we have a regression. I made some data up, and then I made a regression line where, y is equal to beta 1 times x1. x1 is a continuous variable with a normal distribution, plus beta 2 times sex, which is just 1 or 2, all right? So now I have 2 beta coefficients. One of them is with a continuous variable, and the other one's with a categorical. So in my first hypothesis, my hypothesis is that this beta 1 is equal to 0. So how am I going to test that? So what I do is I fit one regression model where y is equal to alpha plus beta 1 times x1 plus beta 2 times sex. And then I fit a second regression model where y is equal to alpha plus beta 2 times sex. So I'm not controlling for my x1, right? I'm only controlling for my sex. And then I plot my x1 on the x-axis, and I plot my model residual on the y-axis. So if there's no association, then there won't be any association between my predicted residual and x1, all right? And then I just plot that, and I say, okay, is that an association? Okay, and then the way it's very strong. I mean, it's very obvious that there's an association between x and y, okay? And then if we wanted, I didn't actually make 19 null plots for this one, but you would just make 19 plots, and you can scramble the x1 data, Okay. Or I could, because I generated the data, I could, but normally you don't have generated data. You can generate the null. If you know the data is more or less normally distributed, you can calculate the mean and standard deviation. You just generate your own data. And then you throw up 19 or 10 plots, one of which is real. All right. And then the second plot is testing the hypothesis that beta 2 is equal to 0. And it's the same thing. You fit the model, a reduced model. You fit a reduced model that does not have the sex term in it, and then you just plot the residuals. Yep. And they're different, so it's pretty obvious. All right. Okay, so this is looking at, they did experiments with the Mechanical Turk service on Amazon, where they put up the visual lineups and they had just random people tell them which plot is different. And then they calculated to see if how good are people at doing this. And yeah, it is in fact, it works. People are pretty good at this. So if you have one person and they're looking at 20 plots and they find it, then your p-value is 0.05. If you have 20 plots and you have 2 people look at it and only one of them finds it, well then it's not as strong in the association because only one person found it. But it's 0.0975, etc. And then it just is showing that yes, this does actually work. All right, so here's another one. What this data is flight delay times at the Albuquerque airport. So it's a radial grid system, and the farther you are out from the center is the longer your flight was delayed. All right, so the middle is 0, your flight's not delayed. As you go out, the flight delay is longer. And then you have the polar coordinates because it's looking at north, south, east, west, all right, and the direction of the wind. So is there an association between the direction that the wind is coming out of and the delay time and the airplane arrival? And the question is, can you pick it out? Anybody see anything?
Wind flows west to east. Looks like the line's going to the left.
Somebody said some numbers? 4. All right. Okay. Now that plot does test the hypothesis, but then they said, well, that one's kind of hard for people to see. Let's try this one. So this is the same data, it's just plotted differently. Anybody see one that's different there?
Is it just histograms?
Other box plots.
Okay. That's at number 4.
Number 4? Okay. So which I prefer the second row. I like looking at the box plots more. Which graph do you folks like better?
Second.
Do you like the second row better?
The second
No.
row. Like the second.
Yeah. Well, it is number 4. Number 4 is the real data. I'm actually really impressed that somebody got it from the top row because I couldn't see it from the top row. I thought it was hard to see. But then in the second row, yeah, you can see it a lot better. So again, just the point is that how you plot your data is going to have an impact on the ability of people to see the associations. All right, so how do you make null plots? Well, if you have a categorical outcome and you know what the distribution of your outcome is, like well, this should be group A 20% of the time, group B 30% of the time, and the other 50% of the time they're group C. Well, then you just generate random numbers, and whoever is less than 0.3 is an A, 0.3 to 5, 0.5 is B, and 0.5 and above is a C. So you just make stuff up that way. If you have a continuous outcome and you know how it's distributed, and you can simulate that, that's another option, just make it up. And the other option is if you have data that's, the distribution is complicated, and it's hard to simulate true data, then instead you just break the association between your outcome and your predictor data. So you just generate random numbers, sort by the random number, and then you set the outcome equal to the vector that was your outcome originally. And you just do that repeatedly. And then you have null data. And then you can make your however many plots you think you're going to need, depending on how many people you're going to show them to. So if you show the plots to more people, you need fewer plots. If you're showing them to just 1 or 2 people, you need more plots. Because if you have a jury, then you're more likely to get the right answer, as opposed to just one judge who's looking at it. All right, the other reason I like this is because it can get people away from statistical significance, and it can focus people more on the clinical or the business significance of what you're finding. So here, which one is different? Yeah, it's difficult to tell, isn't it? Number 4? No, wise guy.
It's like 42, it's the number of the universe.
3? Yeah. Number 9. All right. But yeah, this was some work that we did that customers did not approve. So no. And actually, it is a statistically significant model, but it's not good enough for them. And so that's why I say if you need a data lineup, it may be too late. Because a lot of times, what people really need is something that's a good model, and that really finds something that's meaningful. So while I really like the method, it also brings up the question of if you need this, it may already be too late. Okay, now here's another one. Which one is it here? Yeah, right? Number 5, yeah. Right, so that's, and here, there's several reasons why this one's so much easier to see. If you look at the y-axis here, our counts are much higher, and it's easy to see. And that one has value, so. Okay. All right, so now a couple visualization things, because I'm into visualization. I kind of think of visualization in 2 forms. One is, you're exploring your data. And when I'm exploring my data, I'm my only customer. I don't have a hypothesis, and I'm just doing it fast. And I'm not terribly worried about apophenia then, because I don't have a hypothesis. I don't know what I'm looking for. And if I do have a hypothesis, I'd probably be more careful. And then there's communication. And that's when we're focused on the consumer. We have to make sure it's well labeled, that they know what it is. And it has to support evidence-based decision-making. And that's supporting evidence-based decision-making is why I like the lineup protocol, because you can help people focus on real evidence as opposed to evidence that they just want to see. All right, and then I had some names. Okay, so Florence Nightingale. She was the first female member of the Royal Society of Statistics, and she was also an honorary member of the American Society of Statistics. And so she is known kind of as, this nurse, but I mean, she was an epidemiologist. So, I have to call her out because that's what I do too. And she was successful because she had good data and she presented it well. Actually, her presentations now, when we look at them, the one I have here isn't really maybe great, but it works. So let's look at that one real quick. No, that site can't be reached. Well, we'll get to it in a minute. There it is. Okay. So in this slide, this is the diagram of causes of mortality in the Army in the East, which is where she was doing her work. And the red parts of the diagram, that's soldiers who are killed in battle. Okay? But you'll see that most of the soldiers who are dying in the Army in the East are dying from the kind of gray causes. And what that is that's typhoid, tuberculosis, dysentery, cholera, okay? And so she was saying, you know, what's killing the Army is poor sanitation, poor hygiene, and malnutrition. And then people looked at that and said, oh my gosh, she's right. And we're able to substantially fix the problem. Oh, too far, okay. And then some other names that I've learned over the years are Bell Labs and William S. Cleveland. And they were kind of back in the 50s doing a lot of visualization work. And then there was Leland Wilkinson, and he wrote a textbook called The Grammar of Graphics, which I tried to read, and I didn't get very far. So he did a lot of the first really academic work on visualization. Well, no, I shouldn't say that. I mean, that was basically his whole career. And he also wrote the first statistical software program, which was known as Ttest. And then he went to work for SPSS. He was at SPSS for many years. And then he went to work for Tableau. He was at Tableau. And now he's at H2O. So he's been in the area for a long time. And on the website, on the meetup website, there's a link to a short 8-page paper that he wrote. Now that one you can get through, and it's really worth it. It's very concise, it's very focused, and very useful. I really like that one. Then there's Edward Tufte. Who knows Edward Tufte? You know Tufte. Okay. Have you read this book yet? Part of it? Yeah. It's a good book, right? Yeah, okay. This is called The Visual Display of Quantitative Information, and I brought it because it's unlike The Grammar of Graphics. It's easy to read, and it's also very informative. Tufte is a very opinionated guy, would you say? Yeah. He's very opinionated and he's very critical. So I say that, you know, you read Tufte to learn what not to do. And then you read Wilkinson to learn what to do. All right? Yeah. And then, well, actually, the Wilkinson, you just need to read the 8-9-page thing. It's much better. And that's actually quite good, but a little bit thicker. Okay, and then, so ggplot. ggplot is the implementation of the grammar of graphics in R, all right? So Hadley Wickham, he studied with Di Cook, but he's also very familiar with Wilkinson's work, and then he took that idea of there being a grammar to graphics, that there is a structure to apply, that you can break it down into elements, and that then you can program those elements as objects in R. And so that's what ggplot is. And I didn't start using ggplot, and it is occasionally frustrating, but it does work really well. So ggplot is the implementation of the grammar of graphics. Okay, so this is from Wilkinson's Encyclopedia entry that I linked to on the site. And it's just showing a hierarchy of visualization. So this is, what are people best at seeing? And so what people are best at seeing is a position along a common scale, and then position along non-aligned scales. So like if you see something that's a small multiple, length, angle, slope. And that's one reason area and volume, why Tufte and some others really go after pie charts and say that they're just, you know, they're from the devil. So. All right, and then color being the worst. And what that means when he says color is the worst, he's specifically talking about continuous scales in color. I mean, color can be quite useful for representing categorical data. But if you're trying to use it to say which one is higher, which one is lower, it's not very useful.
My favorite, I did one like that. I was just doing an interface for something. One was green and one was blue. I showed it to a guy I worked with. He was like, I'm blue-green colorblind.
Yeah.
Can't tell the difference.
Right.
I was just sort of like, funny. What is that?
Right. Right. And then there's tools like Color Brewer that help you pick out scales or color schemes that are better for people who are colorblind, etc. All right, that's it. So, questions about it?
I haven't read that proposal. Did they talk about those 3D graphs? Like, I always hesitate to plot my data into a 3D image because I think it's too much.
Yeah.
Sometimes it's too much, and especially for busy people, they use 3D, and it is like sometimes it got lost.
Yeah.
And sometimes it is valuable, but I don't think it is very common. What about the
Ttest is very opposed to 3D.
Yeah.
And there's really no reason to use it. It actually makes the data harder to understand as opposed to easier to understand. So if you think of how a 3D plot is, it has a corner and it has depth. But then you have to ask, well, do I read the scale from the front of my column or from the back of my column?
Tough. And made a comment on use the example on Excel. In Excel, we have a 3D.
Right. Right. Yeah.
Yeah.
3D. I try, but then I always like, I don't want to present that in 3D. because all the questions will come up like, okay, can I see the depth? Can I see the height? And unless you can change, I mean, you can have like a 3D software that you can like rotate it, you can use it the high tech.
Yeah, there's really no reason to do 3D.
Yeah, that's,
No.
So far, I have.
Yeah, and even if you're trying to do something which is in fact 3D, a contour plot would probably be better than a.
Yeah, in the R they have zero or they have option for using 3D.
I've never used 3D in R. Have you ever used 3D?
So
I've
now
never-
3D.
No.
I use like a active, like a animated,
Not 3D, no. Yeah, I'm with you. I don't do 3D. In fact, if I see somebody who does a lot of 3D, I kind of take points off. I'm like, they don't know what they're doing.
Yeah.
Yeah, what about the animated plots or maybe interactive graphics? Yeah, nowadays.
I've not done any of those, so I like many of them when I see them. I've just never done it. I know that Shiny will do some of those.
Right.
And
Yeah, we are
we should-
trying to, we are working on a lot of projects, using Shiny to show that present outdated to the clients.
Yeah, because the interaction can keep people looking at it longer and show trends more easily. I've just never done this. But now I know the call.
So can you share with us like what is your top 3, let's say, your favorite graphics? Pie chart, my chart, and
Line charts.
line chart.
Yeah.
It's your favorite.
Well, I mean, obviously it depends what you're trying to show, doesn't it? So, sometimes you have to map things. Sometimes it has to be a line chart. Sometimes it has to be. But, a lot of the customers that I imagine that many of us have are not the most sophisticated graph readers. So keeping it simple is frequently important. Because I've done charts before. I mean, I have trouble showing people box plots. I love box plots. But I have to teach people how to read them.
One of the visualization that I find my clients love is a map. And for example, like Tennessee or county, and then you have different color for like, let's say, mortality rate in different counties. They love it. days of my work, extra hours of my work, but my clients, I find that period accounting, they almost like, oh, that's cool, yeah. Actually, sometimes I said, well, it's not for me or give you extra information. Just if you can have my lineup, my Davidson County, Wilkinson County, and then you have the water, it's more or less the same, but they really like the map.
Well, you can't sometimes see things in a map that you can't. I mean, if there is geographic information, map is helpful. Like clustering or anything like that.
Yeah, when customer, oh,
Yeah.
they love it. Yeah, they can find out like, okay, these are the customer of this county that have the like lowest income, something like that.
Right, opioid deaths in the state of Tennessee.
Yeah.
Map it, and it's better, yeah.
How they map it by address or?
Well, not just by county. I mean, you might be able to get it down to census tract, but probably county. Because there's not that many of them. Yeah. All right, well, that's all I got.
Thank you.
All right.
And thank you, Rachel, that you mentioned about that there are several references links and links to several articles.
Yeah.
It is available at the website. Right.